All right, this is for the first homework assignment in the parametric chapter, and I'm doing the notes and the homework kind of at the same time to save a little bit of time because we've lost so much this year from snow. So the first thing it wants us to find is dy dx. So looking at that, dy dx, it's the same thing as what we saw in polar. You're going to look at dy dx is going to be the same thing as dy dt over dx dt. So dy dt is 3, dx dt is 10t, and they wanted you to evaluate this when 10 is equal to 3. So let's see, that would be 1/10. Now it wants the second derivative. So the second derivative is definitely going to be a little bit different. And it's really strange the first couple of times you see it, and then you just kind of get used to it. So if I want to take the second derivative, that means I want to take the derivative of the first derivative. But looking at our first derivative here, it is not in terms of x. So we can't really take dx dt because that's a constant in terms of x. So what we're going to do instead is we're going to find the derivative with respect to t of the first derivative and then divide by dx dt. Now when you do that, if you look at this relationship right here, which would be d dt multiplied by the reciprocal, which would be dt dx, you see that you are left with the derivative with respect to x. So what you want to think of is it's the derivative of the first derivative divided by dx dt. So here my first derivative is really 3/10 t to the -1. So when I take the derivative again, I'm going to get -3/10 t squared. So this right here is the derivative with respect to t of the first derivative. And then we have to divide by dx dt, which again is 10t. So this is dx dt. So when you simplify that, we're now going to get 100 over t cubed, and then we're evaluating this at t equals 3. So it's going to be 1 over 900 negative. All right, same thing with the next one. So we want to find dy dx, which of course is going to be dy dt over dx dt. I know you dislike writing this, but on the AP test, they need to see it. So there's a derivative of dy dt, the derivative of dx dt, which we can simplify a little bit. Remember, you always want to try to simplify that first derivative before you take the second derivative. Now remember, the second derivative is going to be the derivative of the first derivative with respect to t. So that's 2/3. And then again, divided by dx dt, which was 3. So our second derivative is 2/9. And they wanted us to evaluate, they get this at t equals 1, so that would really be 2/3 minus 2. dy dx is again the slope of the tangent line. This second derivative, again, is talking about concavity. So it's all the things you saw in Calc 1, just a little bit different. Just like with polar, I can still talk about dx dt, which would talk about your motion right and left. And we can talk about dy dt, that would talk about your motion up or down. So same thing here, we're going to find dy dx, which is dy dt over dx dt. So when I take that derivative, we're going to have 1/2 out in front, and it's going to be t plus 3 to the -1/2 power. Same thing with the next one. And again, we're going to want to simplify this as much as possible. This is the same thing as the square root of t over the square root of t plus 3. So my value of my first derivative at t equals 1 is 1/2. Now to find the second derivative. So remember, you're going to take the derivative of the first derivative. Now here we got a quotient rule and chain rules. So the derivative of the top, copy down the bottom, minus the derivative of the bottom, copy down the top, all over the bottom squared. And then again, remember this part is just the derivative of dx dt, the first derivative. Then we have to again divide by dx dt, which was 1 over 2 root t. Now I could try to simplify this, but they want us to evaluate it at 1, which looks like it's not too bad to do. So let's see, plugging into here, 1/2 times the square root of 1, which is 1, times it by the square root of 4, which is 2, minus 1/4 times 1, all over, let's see, that'd be 2 squared, so 4. And then again, 1/2. So let's see, I could just lots and lots of fractions to simplify, but just leave it like that. Again, dy dx. This time it's going to be dy d theta over dx d theta. So 3 cosine theta and minus 3 sine theta. And if I'm evaluating this at pi over 6, our first derivative is then 3 root 3 over 2 and negative 3/2. So it's just going to be negative root 3. And to find our second derivative, so this is really minus cotangent theta. So when I do the second derivative, the derivative of cotangent is minus cosecant squared. So it's going to be positive cosecant squared theta all over negative 3 sine theta, which would be 1/3 cosecant cubed, sine cubed theta. And then we're plugging in at pi over 6, and at pi over 6, sine is 1/2. So you're going to have negative 1/3 times 1/8, or negative 8/3. Okay, so now this is applying some of the parametrics. So they gave us a parametric equation, which has got x in terms of t and y in terms of t. Part A is exactly what we just did. So dy dx is going to be dy dt over dx dt. dy dt is 3t squared. dx dt is negative 2. So we can simplify that a little bit. That's the same thing as negative 3/2 t squared. And then it wants the second derivative. Remember the second derivative, we're going to find the derivative of the first derivative, so negative 3t. Then we're going to divide by dx dt again, which was negative 2. So our second derivative is 3/2 t. Part B. It's asking for the equation of the tangent line when time is equal to 1. So we already calculated what the slope formula was. So now we're going to plug in 1. So our slope is negative 3/2. But we also need to find our points. Our points, you're going to go back up here, and you're going to plug in the time that we're going to be there, and that's going to be at time equals 1. So our point is going to be negative 1, 5. So our equation of our tangent line is y equals 5 minus 3/2 x plus 1. Part C. It's asking whether the tangent line lies above the curve or below the curve. Well, looking at our second derivative is positive, which is implying that our function is concave up. So if our function is concave up and we're taking a tangent line at any point, the tangent line is going to completely be below the concave up part of it. So the tangent line is an under approximation. So tangent line is below. So tangent line is an under approximation. Six is exactly the same. So first thing, dy dx, which of course is going to be dy d theta over dx d theta, which is going to be 3 cosine theta minus 4 sine theta, which is the same thing as negative 3/4 cotangent theta. So then our second derivative is the derivative of the first derivative So it'd be negative cosecant squared, so now positive cosecant squared theta divided by dx dt, which is minus 4 sine theta. So then we plug in 3 pi over 4. And then in part B, it's asking us to find the tangent line at theta equals 3 pi over 4. So we're going to take the first derivative and evaluate it at 3 pi over 4. Let's see, 3 pi over 4 is in the second quadrant, and sine and cosine have opposite signs. And so that's going to be positive 3/4, because we would have had negative 3/4 times cosine, which is negative root 2 over 2, divided by sine, which is root 2 over 2. So that just leaves us with positive 3/4. So that's your slope, and we also need a point. So our x point at 3 pi over 4 is going to be negative root 2, and the y point is going to be 3 root 2 over 2. So now the equation of the tangent line is 3 root 2 over 2 plus the slope, and then x minus the x coordinate. Part C, determine if that is going to be concave up or concave down, because we want to know if the tangent line is an over or an under approximation. So let's see, sine is positive in the third quadrant, so we know that the second derivative here is going to be negative, which implies that it's concave down, which implies that the tangent line is going to be an over approximation. Find all the spots It's asking, use a graphing calculator to represent the parametric equation. Find the equations of the tangent line at the point where the curve crosses itself. So when you put this in your graphing calculator, it ends up looking like this. And it's crossing itself at the point 0, 0. So looking at the first thing, we got to determine when x is equal to 0. That would be at 2 sine 2 theta. So we would have that x is equal to 0 at 0, pi, 2 pi, so on and so forth. Y has got to be 0 also. That happens at 3 sine 3 theta. It's got to be equal to 0. So that would be at theta equals 0, pi, 2 pi. And over here, when we solve for theta, we have to divide everything by 2. Now I need both the x and y coordinates to be 0. So the only place that both happens is at 0, pi, and it would happen again at 2 pi. But 0 and 2 pi are the same thing, reference angles. So we want to find the equations of the tangent line. So we're going to find our dy dx. So the derivative would be dy dx, which is 3 cosine theta, over dx d theta, which is going to be 4 cosine 2 theta. And we're going to evaluate this at 0. So the first one's going to be 3/4. We're also going to evaluate this at pi. So at pi here, we're going to have 3 cosine of pi, which is negative 3, 4 cosine of 2 pi, which is positive 1. So those are 2 different slopes. So our first equation of the tangent line would be 3/4 x, and the other one would be y equals negative 3/4 x. We're going to find the horizontal and vertical tangents. Okay, so remember what a tangent or the slope looks like in parametric. It is dy dt over dx dt. So if we want a horizontal tangent line, we're looking for where dy dt is equal to 0 and dx dt is not equal to 0. So we know that it's horizontal when time is equal to 0. The vertical tangent lines are going to come from when the denominator is equal to 0. So here dx dt is equal to 3. That's never equal to 0, so we know that there's no vertical tangent lines. And it asked for the points where this happens. I know it happens at time equals 0. We'll have a horizontal tangent line, and the point will start at 1, 0. Same thing over here, horizontal. We're going to look at dy d theta, or dy dt. So dy dt is again 2t, and we're going to set that equal to 0. The only time that happens is at 0. We look at the vertical tangent lines. That's where dx dt is equal to 0. Notice we can factor out a 3. And then you're left with the difference of squares. So there are two places where you have vertical tangent lines, at 1 and -1. And again, they ask for the points. So the point for the horizontal would be 0, -3. For t equals 1, we're going to get -2 and -2. And for t equals -1, you're going to get +2 and -2. Again, same thing. So dy dt is going to be your horizontal tangent line, where that's equal to 0. So that's where cosine t is equal to 0, and that happens at t equals pi halves and 3 pi halves. And dx dt would be minus sine t is equal to 0, and that happens at t equals 0 and pi. And then now we can find all those points. So at pi over 2 is our first point, and that would be at 2 and 0. 3 pi over 2 is our next point. So again, that'll be at 2 and then -2. At time equals 0, we're going to be at 3, -1. At time equals pi, we're going to be 1 and -1. And the last one, dy d theta is equal to 0, is where we'll have that horizontal tangent line. So for cosine theta is equal to 0, and that happens when theta is equal to 0, pi halves and 3 pi halves. And the other one is dx d theta equal to 0. That's going to happen when minus sine of theta is equal to 0, and that's going to happen when theta is equal to 0 or pi. And again, we can put all those in. So at theta equals pi over 2, the point is at 0, 4. At 3 pi over 2, the point is at 0, -4. At theta equals 0, the point is at 4, 0. At theta equals pi, it is at -4, 0.